And to quantify that, you need to know the likelihood of a false positive, which is the probability that that data was generated given an abiotic pathway. And you basically compare that to your prior likelihood for the probability of life. So all this seems very high level. So what is P life? Well, that's a great question. And you actually need to know that if you want to talk objectively about biosignatures. So basically, you're trying to weigh the probability that what you're looking at is life against the probability of some rare abiotic pathway. So something like volcanoes or tectonic plates, something like that that can generate the same signal in the atmosphere. But the big problem is that we have no idea what the probability of life emerging in a given planetary context is. So it could be small, you know, like 1 in a million, but it could also be astronomically small, like 1 in 10 to the 22. And so if it's astronomically small, then the chances of an unknown abiotic pathway are orders of magnitude more likely than the chances of life being responsible for that observation. So that's kind of how I got led down the path to studying life. So I took this pretty seriously as we really need to understand life and the emergence of life better if we're ever going to understand biosignatures outside of our solar system. So my dissertation research started with the hypothesis that information processing is what differentiates living and non-living matter. So there's this idea that systems that we think are alive have more information processing ability than systems we think are not alive. So here on the left, this is just oil droplets. And if you study their dynamics through time and space, you'll see that they do relatively complex patterns. And it kind of looks like something that could be alive, although we all know that it's not. But basically, this is a complex spatio-temporal system. And then in the middle, we have ants. This is a colony of ants during nest migration. And then on the right, we have the human brain, which is arguably the most information processing, aside from potentially a computer, that we have. And so I was basically just wanting to take these model systems and apply some measure of information processing to test this hypothesis that systems that aren't alive don't process information, and systems that are alive do process information. Just to kind of get at this, this notion that life really has to do with the way systems process information.
Can I ask a quick question here? So I've seen philosophers talk about rocks as information processing systems because they, process the decay processes of rocks. I didn't believe it, but how do you define information processing?
Yeah, exactly. So information is one of those words that means a lot of different things to a lot of different people. Here, what I mean by information processing is basically you have some sort of computation with inputs and outputs, and you're looking at how those inputs get transformed to outputs. And so basically you need an abstract computational description to even measure information in these systems. Does that make sense? Or do you want me to go a little deeper into that?
Yeah, a little deeper would be good.
Yeah, so my starting point is transition probability matrix. That's what all of these information processing measures are going to act on. And here I'm basically using information theory, so like Shannon information, to measure information processing. So I need a transition probability matrix to even talk about this. And for something like a rock, if you could define a transition probability matrix, then I could measure the information processing. So if you want to talk about like how the crystals in the rocks decay over time through radioactive emission or whatever, if you have a transition probability matrix for that, I'm willing to calculate the amount of information that that rock is processing. But it does need to start from some abstracted description of the rock.
And the transition probabilities are between states of the rock?
Exactly. And the states are something you have to define.
Okay.
Yeah.
I'll
So
suspend my disbelief now.
yeah. Okay. Yeah. Fair enough. So these are different measures of information processing, and this would maybe help as well, Gary. Like I'm trying to use one of these measures. So there's all sorts of information theory measures. Basically, all of them need a transition probability matrix or some finite state description of the system to work. And so your question kind of gets at this first step of abstracting. So how do you take an actual system that you're observing and abstract it into a mathematical description, which is this transition probability matrix? And so that step I'm not as clear about, but where I start all of my research is with these transition probability matrices. So I'm not as interested in the first step. I'm more interested in once you have a transition probability matrix, what do these measures say? So these are all the different measures that could work for the project that I was interested in. The best by far was integrated information theory, because not only is it a measure of information processing, it's also a measure of consciousness. So that was a surprising benefit to this measure of complexity, because consciousness is pretty much a measure of life. So I don't think it's hard to argue that consciousness is a sufficient condition for life. You can take the stance that maybe you can have consciousness without life, but it's pretty easy to argue if you have a measure of consciousness, you have a measure of life. And more specifically, there's something called the life-mind continuity thesis, which says that cognitive processes are an enrichment of the organizational principles and processes definitive of life. So under this view, consciousness is actually the same process that creates life, just more enriched and distilled. So basically, life is on a spectrum from non-living to life to conscious life. It's all the same spectrum. So in this context, basically, the argument is that measures of consciousness are measures of life. So I don't need to invent my own measure of life because we have these tailor-made measures of consciousness, such as phi in IIT.
Can I ask a question now?
Yes.
This continuum from life to conscious life, what's the step just before it?
I was just saying it's like non-living to living to conscious life.
Yeah. What I understand the attempt to quantify properties of life with this transition probability matrix. But where does consciousness come into it? And in just a few words, without getting into controversy, what on earth do you mean by consciousness?
Okay, so my understanding of this life-mind continuity thesis is that you have matter to start. So you have atoms, molecules, and when that matter gets organized a certain way, we call that life. And that same organizational property, if you scale it up or perhaps clean it up, you get things that we would refer to as conscious life.
That sounds sort of arbitrary to me. I understand what life is. It's got certain properties. What are the properties of consciousness that you have in mind? And what's to prevent a Buddhist monk from saying, actually, no, there's 4 points along this continuum. You start with non-living, then you get living, then you get conscious, and then you get spiritually realized consciousness. Why can't we go on like that?
Right. So your first question, so what are the properties of consciousness? I'm not sure. I think that there are things that we all agree are indicative of consciousness. So self-report in another human, I think that that's pretty much widely accepted. Anything beyond that starts to become a little less clear cut. But I think it's basically, you know it when you see it, and it's grounded in our own things that look like us, we associate consciousness with. So I don't have a great answer, but that's kind of how I frame it.
Answer. I think it's a great answer. You said you know it when you see it, because it feels like something to see something. And if you had simply said all you mean by consciousness, conscious states, is felt states, you have had me on board.
Great, great. Glad to hear it. And then in terms of what if there's 4 points along the spectrum, I think that the spectrum is a continuum. So I don't think it's phase transitions between discrete, qualitative states. I think the idea is that, yeah, there's a continuum here, and there's states all along this continuum.
Okay, go ahead.
A quick question before you move on. Can you hear me?
Yep, I can hear you.
Yeah. You say it's a continuum. Do you think it's possible that large language models have consciousness and that like a little bit of consciousness?
So I'm kind of just a skeptic in the sense that I don't know. I don't know at all. So I'm of the opinion that I'm trying to just do some things mathematically that provide more points of evidence to make those assessments. I have no idea if large language models are conscious or not, unfortunately.
Nobody else does. You're not alone. Go ahead, Jake.
Yeah, thanks. Okay, so let's talk about IIT. So this first part's going to be slightly technical, but that's because my first results are technical. And I think the results are interesting enough to justify this slight technical digression. So what is integrated information theory? How could it ever claim to measure consciousness based strictly on a transition probability matrix? Those are my questions when I heard about what it was. But the thing that kind of got me on board is that it's a preeminent theory of consciousness. So many very smart, very accomplished researchers endorsed it. Like I remember Max Tegmark, sounds like Mike Levin. So I was convinced basically just by the fact that smart people were endorsing it. And also, if you see the citations per year for all these different rival theories of consciousness, you see that this is basically the most popular theory of consciousness we have. So I hadn't done any research in consciousness prior to this. And so when I realized that this is kind of the gold standard for consciousness research, I basically assumed that it was right, and I had to learn how it works. So the first thing that you learn about IIT is that it's very mathematically rigorous. And by rigorous here, I just mean it's just mathematically intense. It's not like anything else I've ever studied with different physical theories. It's just a lot of math, and it's kind of all cobbled together. And the words are supposed to map to things like phenomenology, and it's very difficult to grasp. Another claim to fame is that it's experimentally falsifiable. So that's stated all over the IIT papers. And the last thing is that it gives you a single mathematical measure of consciousness that acts on any discrete dynamical system. So this is why IIT is so popular, in my opinion. Is just because it gives you the answer, right? You just put in your transition probability matrix, it outputs consciousness in this single measure phi. So how does it do that? Well, I guess first I should go back to this whole idea. Basically, I can just put these systems into phi. It'll spit out my phi value, and this is what I could use for this whole project that I was working on, which is I wanted phi values for these systems. I wanted to write a paper that says these systems have low phi value, these systems have high phi value. It all makes sense given what we know about consciousness and life and that sort of stuff. So that was the motivation.
So it's like hi-fi.
Hi-fi, correct.
Sorry. Couldn't help myself.
Oh, you're good. All right, so how does the measure work? It's basically a measure of emergence. So, or it's trying to be a measure of emergence. So phi is the amount of information generated by a complex of elements above and beyond the information generated by the parts. So, for example, on the left, you have a toy model of the corticothalamic system, which is highly integrated. There's lots of feedback connections, and it has a phi value of 4 in this system. This isn't actually a phi value. This is just like to help you conceptualize what you're measuring. And then on the right, you have the cerebellar system. It's more separate. So there's small complexes of integration, and then they're sparsely connected. And so within these complexes, you have relatively high phi values, like 1.8 for this complex here. And then between complexes, you have phi equals 0.4. So you're basically trying to measure how integrated and how sparsely separated things are. And so to do that, you're trying to measure the feedback connection. So phi is a measure of the extent to which feedback is present between components in a system. So I'll keep returning to this because the important thing here is that you're really measuring feedback. So to calculate phi, you can't do it for the human brain. It's way too big of a system. These transition probability matrices need to be really small. And so the phi values can only be calculated for systems of like less than 10 bits. So that's like saying less than 10 neurons. So we're very far from using an actual human brain. Instead, we use simple systems of logic gates, such as these 2 bits, this 2-bit system where there's a logic gate that's an AND gate and a logic gate that's an OR gate. So this is a huge departure from how most of you probably think about measuring consciousness. We're basically not talking about biological systems or anything. We're just talking about these toy models made of simple logic gates, because really what we're doing is theory building, and we're trying to get a measure that measures feedback between these bits, Q1 and Q2. And so the first step is you break the system up into parts, and you break all those parts up into parts. So here for a 2-bit system, you have the system as a whole, which is Q1, Q2, and then you have each individual bit, Q1 and Q2. Each of these parts is called a mechanism. So I'll be using that word. And if I use other IIT words, please interrupt and ask what I'm talking about if I haven't defined it. So I apologize in advance if I slip into IIT talk. So each of these parts is a mechanism. And in step 2 of the calculation, you ask how the mechanism constrains the past and future state of other mechanisms. So what this means is if you know the current state of the Q1 bit, let's say you know that Q1 in its current state is 0, you ask how does that constrain the probability of what the system as a whole could have been. What could Q1, Q2 have been in the past? And so you know Q1 current 0, so that means the only possible values for Q1 and Q2 in the past were these 3, because Q1 is an AND gate. So if it's 0, you know that in the past it wasn't 1, 1, otherwise it would have been 1. And so you use this to build a probability distribution. So you basically have a uniform probability over the 3 possible states. And this is the cause repertoire. So my first result is going to concern these cause repertoires. So I know it's technical and I apologize for that, but there's basically no way around it. So this is the cause repertoire for this mechanism and this specific element, Q1, Q2. And so the whole aspect of integration is you ask, what happens if you cut the connection between Q1 and Q2? So rather than Q1 constraining Q1, Q2, you just let it constrain Q1. And so here, Q1, the possibilities are 0 with probability of 2/3 and 1 with probability of 1/3. So that's your Q1 connection. And you need to expand that by assuming that it's just random noise over Q2. And if you do that, you get a different probability distribution. And you measure the distance between these probability distributions. And that gives you your first little phi value. So this is the first step in the calculation, is you get something called little phi, which is the distance between the mechanism constraining the cause repertoire and the mechanism constraining the cut version of the cause repertoire. And that basically tells you how important was feedback for this one connection here. So little phi is different than big phi. Big phi is going to be optimized over all these different little phi values. Okay, so that was one part of the calculation. This calculation is massive. You need to do this process for every possible mechanism in the past. So that's called your past purview. So you repeat this and you get these different cause repertoires for each element of the past purview. And you find that they each have a little phi value of 1/6. So here's the crux. The next step is applying the exclusion postulate. So the exclusion postulate states that a mechanism can contribute to consciousness at most one cause repertoire, the one having the maximum value of little phi. So in the slide I just showed, all of these cause repertoires had the same value of little phi. And so this was the first thing that kind of drove me crazy when I was trying to do this calculation. I had started with this and or system, and I sat down to do the calculation, and I got to this point where I was supposed to choose one of these cause repertoires based on their little phi value, but I found that the little phi value was the same for all of them. And so the question is, well, what if the phi values are the same? And there was nothing in the IIT paper that says what to do if the phi values were the same, but it makes a big difference because if you choose this cause repertoire and you carry this distribution forward in the calculation, the actual distribution matters. So after you go through the next steps, which are further optimizations, you get a big phi, which is consciousness of 0.09. But if you choose this one, you get 0.25. And if you choose this one, you get phi equals 0, which is unconscious. So you get conscious or unconscious depending on which of these cause repertoires you choose. And so the first part of the results is that you get different phi values depending on the cause repertoire. So that's a big problem because, like I said before, you need to do this optimization over and over again for all these different combinatorial combinations. And basically, step 5, you do the same thing for the future states. How does the current state constrain the future? Step 6, you repeat for all the mechanisms. So now you go to Q2, Q1, Q2. And then in step 7, you basically duplicate the entire system, but you imagine that this connection doesn't exist anymore. And you do all those calculations again. And so the result of that is a ton of different phi values that result depending on which of these cause repertoires you choose. So here you have all different phi values corresponding to different choices for your cause repertoire, and all are equally valid because they all have the same little phi value. So that leads to this first result, which is that for this simple system, which was the first one I ever tried to calculate phi for, you get 83 different phi values spanning the entire range of possible values for what you'd expect. So here on the y value, here on the y-axis, this is the phi value, big phi. And then on the x-axis, this is just rank ordered. So these are all possible values. In orange, this is the original system. In blue, this is the partition system that cut. So that's just another optimization you have to do. And basically the one value that you get from phi, which is the code that you can use to calculate phi, is shown here as a white X, but it's just arbitrarily selected from this huge range of possible phi values. So I'll pause there just in case I lost people, but that's the first result, is that you have this non-uniqueness problem.
Can I ask a question about why you originally used this? You took IIT and phi as being the best of the lot. Okay?
Yes.
Is that in itself a recommendation?
I mean, I would not recommend anyone use IIT for anything. So,
You
yeah,
chose it because you thought it seems to be the best measure of consciousness.
for sure. I think an outside person, which I was, if you look at theories of consciousness, IIT rises to the top in terms of citations, in terms of endorsement, in terms of like just overall, I don't know, it just looks really good. I think that's changed slightly in the past year or so, but I think an outsider would land on IIT as the sort of gold standard for consciousness theories.
It's a question of taste. I would, if I got in an area like consciousness, which is so fuzzy and confused anyway, the top contender is probably going to be the worst. I mean, maybe we would have found a quantum mechanics version of it that was even more popular.
Yeah, I think that that's where I'm at now. I would be way more skeptical, but I think I was way more trusting in science at the time. Like I thought that if you're published in journals, that meant that it's probably right. But that was naive of me. I've learned.
Everything you've been saying has been really clear. I just want to thank you for that.
Yeah,
Thanks.
it's extremely clear. I had a quick question about this. Now, it does seem like the graph model you have here is almost trivial. And so one wonders if you had something that had, as you say, you apparently can't do more than 10 states, or I'm sorry, a 10 by 10 transition matrix, which I get 10 states. And if you had a more complex circuit structure, this circuit structure seems to produce different levels of maximum entropy, including 0 and some that are, of course, distant from that. So maybe this is just kind of a floor effect. Have you tried this kind of thing with, say, much more complex graph models than this simple feedback system?
Yeah, that's a great point. And that's a pretty common counter argument to this, is that this system is overly contrived. It's highly symmetric. You're likely to have less symmetry in bigger systems. But we studied that, and it actually is the opposite. So as you get a bigger system, you get a bigger support for your distribution. And so that means you have a lower probability of these ties. However, you also have more mechanisms under consideration, and the amount of mechanisms you have to consider grows much faster than the size of your support. And so the problem actually gets worse as you get bigger and bigger systems. And it also applies to different logic gates, not just and or gates. It applies to like majority gates, which basically, it's a threshold. And the threshold model is most similar to what like a neuron would be. It's basically adding up all your inputs, which I know there's problems with that. So I'll stay out of that whole topic. But we did study it for other systems, and I don't think the problem goes away.
Along those lines, though, there is a whole complexity theory having to do with graph analysis. So if you look at order statistics or some other structure that in fact could indicate feedback and asymmetric feedback, although most of the brain, of course, has a lot of symmetric feedback, and like massive amounts of symmetric feedback. But in this case, you can estimate something about the distributional aspects of the order over the in-out flow of these systems and preserving direction. And that provides a different kind of distribution on this set. Now, I agree with your next comment, which would be, well, that's not this theory. So fair enough. Yeah. But I do wonder why they did it this way. This seems entirely stupid.
Yeah, I mean, I'm with you. I think there are ways to measure things like feedback that are probably mathematically well defined. But yeah, like you said, I'm pretty limited to IIT. I was just trying to stick within the definitions of the theory. But I don't think that there's no good measure of feedback. I think that there are good information theory measures of feedback. And I'd be curious to see what they look like. But yeah, that was outside the scope of this.
Yeah, I appreciate your comment on that.
Awesome. Well, yeah, let's keep moving forward. So then my question was, well, how do people calculate phi? There's all sorts of published phi values. And the first time I tried to calculate it, I found just a plethora of different outputs. And so I started to look at, well, what are people publishing? And it was always the phi value. And so I looked into the phi code, and I saw, well, how does phi handle these ties? And what it does is it just keeps the first distribution. So if phi is less than phi MIP, these values are tied, then your less than sign isn't going to work. So it's just going to keep the first one, and everything else that's tied gets thrown away. And so I rewrote the phi code, or I wrapped it, and I had it find all of these tied cause repertoires and keep all of them so that I could figure out what are the actual phi values that are valid according to the technical definition of phi. And then I applied that to all the systems I could in the literature. So this is a corpus of 10 different systems. And I basically compared the phi result, which was published, and there's narratives built around it. So basically, whenever you have a value, the whole paper is about why this system is conscious. And I reanalyzed all those papers with this phi spectrum code, this wrapper for phi. And here you can see all the different phi values for each of these papers. And importantly, you see that sometimes phi equals 0 is included as well. So like this Marshall et al. Paper, that was a paper where they looked at a biological toy model and they looked at all these different like phi complexes, different systems, and phi equals 0 was just as valid. And I think if phi equals 0, that says that none of this is conscious. And so all this discussion is kind of moot if you consider the fact that phi equals 0 is also valid according to the definition of IIT. So the results of this first paper, which I put the citation in the bottom, is that virtually all published phi values are selected arbitrarily. And so what I mean by virtually all is that we couldn't study systems that were bigger. And yeah, that's pretty much what I meant there. And then like I said before, you get these systems that have phi equals 0 and phi greater than 0, which really means that IIT is just not a well-defined mathematical theory. So it's not predicting conscious or not, it's predicting a whole spectrum of values that sometimes have conscious, sometimes don't. So I did cover this before with the question, but in IIT 4.0, which came out very recently within the past couple of months, they talk about these ties, and they also say that these ties are unlikely to occur in realistic systems. They don't provide any evidence for that claim. And like I said before, I don't think that that's true. I think that this problem is going to get worse with scaling rather than better. So we studied this. There's a small section on it in this paper. But yeah, the scaling goes to infinity as n goes to infinity in terms of the degeneracy, meaning the number of tied states. And then they did go out of their way to correct the non-uniqueness problem in the rare case that a tie still exists, which I don't think is that rare. But basically, they said that if there's ever a tie, then all of the purviews get thrown away. So basically, you don't have a big phi value. Phi is 0 if things are tied. And the reference they point to here is a paper on non-uniqueness from 2019. And this is also something we studied in the non-uniqueness paper. So this Moon solution to non-uniqueness is overly restrictive in the sense that it says that systems like an AND OR gate are not integrating any information. So you have a fully connected AND logic gate taking input from itself and a second input. And it says that that is not integrating information, which to me, I feel like that means that it's not a measure of integration at all. So it's overly restrictive. It's unstable to small perturbations in the sense that you throw everything away, but if it's slightly different, then you keep everything. And then the justification ultimately relies on the intrinsic perspective of the system as measured by little phi. So it's kind of circular and very hard to argue against because it's just assuming that what's the theory says is correct and there's no other consequences to that. Okay, so we're already 45 minutes in, so I'm probably going to speed up a little bit, but I'm also okay if we don't get to the conclusion. So I'll go through this section relatively fast, but you can still interrupt, and I'll just plan on probably not getting through the final section, if that's okay.
You've got time.
Okay, so I want to take a step back and talk about how IIT is supposed to work as a scientific theory. So IIT starts with phenomenological axioms. So that's supposed to be undeniable axioms about what it's like to be conscious. And then it has to translate those axioms into postulates about what sort of physical systems can embody those axioms. And then once you have the physical systems, you can make experimental predictions. And what makes this whole framework valid is that your experimental predictions are supposed to justify this first step, which had to be assumed. So the step from phenomenological axiom to physical postulate, that's the hard problem. So this is a gap that's very hard to bridge, but the idea is that if you get to the right experimental predictions, then that kind of justifies this leap you had to take, this metaphysical leap from phenomenology to physical postulates.
Can I ask you a question? In physics, and your background is in physics, phenomenology is used differently from how it's used in philosophy of mind. Phenomenological theory, like kinetic theory versus a dynamical theory. But in philosophy of mind, phenomenological means a felt experience. There's no doubt. It means a felt experience. It's produced nonsense because people have said that there's phenomenological consciousness and other kinds of consciousness. But if you take what I think is the correct one, which is to say phenomenology is consciousness, that's not the sense in which you're using the word phenomenology, is it?
No, it's not. And I think people have argued that against IIT. So IIT says these are phenomenological axioms, but I think there is room to say that that's actually not phenomenology. These axioms are claims about what conscious experience is like, but it sounds like what you're saying is that phenomenology is something that's felt. It's not something that you claim everyone feels, because then it introduces some ambiguity there.
Yeah.
So yeah, was there a follow-up there?
Well, that's it.
So I'll give you an example of what I think is the most important part of IIT, and that's basically this integration axiom / postulate. So the axiom in IIT is that consciousness is experienced as a unified whole. And so the example they give to help explain this is that your left and right visual field are integrated into one conscious experience. I think that example makes sense. They also give an example of a red apple not being experienced as red and apple. I don't really understand that example at all. But the important thing is that this has to be translated into something physical. And what they translate it into is that feedback is a necessary condition for consciousness. And what feedback means here is feedback connections between elements in the systems, like between neurons in the brain. And so, like I said earlier, phi is ultimately going to measure the extent to which feedback affects the dynamics of a system. And so the question is, well, how does IIT justify that feedback is really what they're talking about with consciousness as a unified whole? And so that was the question here is, this is a big leap, and I'm not sure. I believe that feedback connections are what leads to a unified whole. So to justify that, they need experiments, and IIT makes a big deal about the fact that it can be experimentally verified. And so here's a quote from the IIT 3.0 paper, which says that IIT leads to experimental predictions. For instance, that the loss and recovery of consciousness should be associated with the breakdown and recovery of integrated information. So the experimental paradigm that they set up, they were working with fruit flies. This is an actual experiment that they did. And basically you have a fruit fly that's awake, and then they anesthetize it, and then it's asleep. And the prediction is that if phi decreases when it's asleep, then it validates the theory. Whereas if phi increases when it's under anesthesia or it stays the same, then the theory is falsified. So this is supposed to be a clear experimental prediction. So they ran this experiment, and you can't actually measure phi for these systems, but you can measure proxies for phi that make a lot of assumptions. And that's what they did here. And they showed that under anesthesia, all these phi values, this phi complex disintegrates. And so since phi is lower for when it's asleep than when it's awake, that was validation for the theory. At least that's how it's supposed to work. But where I got confused about this is there's a theorem in automata theory called the Krohn-Rhodes theorem. And what it states is that any deterministic finite state automaton is a homomorphic image of a cascade automaton comprised solely of reset and permutation automata. So I know that that makes pretty much no sense if you don't know anything about automata theory, but you can translate this and basically show that what this means is that any finite state system has a Turing indistinguishable feed-forward version. And so in the context of IIT, that means that every system with phi greater than 0 has a functionally indistinguishable counterpart with phi equals 0. So Krohn-Rhodes theorem gives you a way to get rid of feedback while preserving function. And before I forget, I'm going to call these functionally indistinguishable counterparts philosophical zombies sometimes. So this is where my work intersects with Stephen's in the sense that the type of Turing indistinguishability I'm talking about is actually total Turing indistinguishability, or T3. So there's this level of indistinguishability. T2 is the normal Turing test. It's natural language processing. T3 is same external sensory motor function for all inputs and outputs. So it's a much more precise match between systems. And then T4, you also have the same internal circuitry, and T5, you actually use the same material properties. So I'd like to talk about a concrete example just to help ground thinking. So the example I'm going to use is a toll booth that takes $2 in quarters only. And so what it really is a mod 8 counter. It counts to 8 through 8 internal states. And basically to make this circuitry, you need to assign these functional states a binary coding. So there's 8 states, that means you need 3 bits, and these are just randomly assigned binary states. And once you have your binary states, that lets you build the circuitry. So these are all actual circuits that you can wire up, and if you had a toy toll booth, it could operate a toll booth. But the point is that this encoding leads to a network with feedback and phi greater than 0. Under the Krohn-Rhodes theorem, you have a different way of encoding where you choose your encoding very carefully so that your first bit doesn't depend on the state of later bits in order to operate correctly. So your first bit here is just even or odd. It keeps track of if the state is even or odd. And because of that, that bit just flips back and forth between even or odd. And it doesn't matter what your later bits are for that bit to update properly. Your next bit basically adds a level of refinement and says where in that first even or odd structure you are. So if you're odd, are you in the 1-5 set or are you in the 3-7 set? And so that bit only depends on the first 2 coordinates. And then your third bit specifies fully the system. So it's a really cool way of kind of assigning these coordinates. And it's a very deep field if you're ever interested. You can do a lot of really cool stuff because you can truncate these coordinates and get basically effective theories built from this hierarchical labeling scheme. But the point for this conversation is that under Krohn-Rhodes decomposition, you get a different way of labeling these functional states that gets rid of feedback. And so this circuit down here has no feedback and phi equals 0. So the only difference here was I changed what labels I want to use for these functional states. And simply by permuting those labels, I got rid of all the feedback and I changed the system from conscious to unconscious. So what phi is actually measuring here is the syntax of the computation. So it's measuring what binary label is used to instantiate a functional state rather than what the functional state does within the system. So to return to this, this hierarchy, basically, if you have the same computation, those are going to be T3 indistinguishable, assuming you have the same hardware. And then if you have the same encoding of that computation, those are going to be T4 indistinguishable, which is more of a match than T3. So getting back to the experimental paradigm, we have this fruit fly that was awake, high phi. We have this fruit fly that's asleep, which has low phi, but still non-zero. And if you perform a Krohn-Rhodes decomposition on this system, you would get a fruit fly that's awake, but has phi equals 0. So what this means is that phi for being asleep is actually greater than phi for being awake. So here you have phi greater than 0, the system's asleep. Here you have a philosophical zombie that's awake, but it has phi equals 0. So this should falsify the theory by their own experimental paradigm. The problem is that IIT allows philosophical zombies. According to IIT, the fruit fly that's awake is conscious, but if you get rid of all the feedback, it's unconscious. So basically, the feed-forward system is unconscious because of the integration postulate. That's how it's justified in the theory. But the problem is that that was the whole point of this paradigm, was to test the integration postulate. So we've come full circle, and that the integration postulate is used to defend the results from the test of the integration postulate. So, yeah, that leads to, oh, this is supposed to say the demarcation problem, but basically the key feature of a scientific explanation is to work out what difference it makes to things we can observe if the explanation were to be true. So in the case of the toll booths, we had our conscious toll booths. We did a Krohn-Rhodes decomposition. We got an unconscious toll booth. These systems are T3 indistinguishable. They have the same input-output behavior for all inputs, all outputs. They have the same functional topology, which is just a different way of saying that. And importantly here, they have the same efficiency. So one of the common replies to feed-forward decomposition in IIT is that, well, once you get rid of the feedback, it's really much less efficient because you need more bits to instantiate the computation. And the whole point of this specific decomposition was to show that that's not true. You can get the same, you can get rid of feedback without increasing the number of states needed to instantiate the computation. So that's what I mean by efficiency. And ultimately, it was the same mathematical computation. So if IIT is supposed to be measuring something about the computation being performed, these have that same computation, and so the phi value shouldn't change between systems. So all of that to say the presence or absence of feedback makes no difference to things we can observe in this system. So that pretty much brings me to time. So like I said, I'm okay to just end here. I'll skip through this and just kind of highlight that this has been extremely contentious lately. So I think a few months ago, there was 120 people that signed a letter that said IIT is pseudoscience, basically for all these reasons that I just laid out. And there's a big backlash, and it was very contentious, this whole thing. But I think that the claim of IIT being pseudoscience is valid if you look at the circular logic and the fact that it disagrees with known experiments. So in my experience, IIT is a very grandiose theory. You basically can't understand what it's saying unless you have a lot of time to learn the mathematics, which is very dense. It's very ad hoc. It's filled with heuristics, which is not something that's common in other physical theories. So there's no other theory in physics that I know of where somewhere in the calculation you insert a heuristic about picking and choosing between these different distributions. It's falsified by experimental benchmarks in the sense that you have phi equals 0 when things are awake, you have phi equals 0 during self-report, you have phi equals 0 during no report paradigms. No matter what your experiment is, you can have phi equals 0. There's also inactive logic gates and toll booths that most people would say aren't conscious, but IIT says are. And ultimately, the postulates can't be tested because phi is decoupled from anything that you could use to ground the theory experimentally. So I'll end it there.
That was terrific. Just a sec. Maybe you can unshare so we can see everybody for the questions. Okay.